People here this morning here. But here we are. This is the John Chappell Natural Philosophy Society Science Chat, where I can chat with cool people like James about what is the latest things that's on our mind for science. But you've got some new results you were talking about. What kind of results? Been running some more simulations or something?
Well, I can give it to you in words, and it may work out. There was a study which I sort of replicated with a larger simulated volume that was called Matter Creation Sequel on the Journal of Binary Mechanics website. And since that study was published, I have seemed to have parsed the range from absolute zero quanta density, which I call absolute vacuum, to distinguish it from partial vacuum, all the way up to 1 bit density, which is maximum. Every quanta loci has a bit in the one state in it. That would be maximum possible density. So I've tried to parse this range, and it turns out that from about 0.75 and above, we're in an area which I'm calling a lepton quark soup. And then from about 0.66 up to 0.75 is plasma. From below 0.66 down to, let's say 0.1 is a range where atoms and stuff occur and are formed. And consistent with the some of the theories that I've seen in astrophysics, at the higher densities, in other words, up to more like say 0.66 or 0.6, you get higher Z atoms apparently forming, and that agrees with what we've seen in astrophysics literature, where they're saying a lot of the atomic material like iron and what have you that we have here on Earth was actually formed in these huge explosions.
But why would that lead to higher bit density? Because we know that all atoms fundamentally are made out of neutrons and protons and electrons. I wouldn't think that the bit density would have to vary, presuming that they're made out of the same components.
Well, okay. To get to the punchline, I don't want to evade that question. Hold that if I don't address it properly. But in these experiments, we would set up with randomized seeding of one-state bits in a volume with an initial bit density ranging from near 0 on up to 1 in various steps, like say 0.05 at a time. And when we get down to the lower bit density range, where we are probably operating in our environment right here and now, smaller increments, so that we get a graph that looks pretty good. Now, what happens if you run it in vacuum mode is that any particles with momentum that exist in the simulation can get blown out in vacuum mode, and there's simply bits leaving the simulated volume and are lost, okay? So that after a time, any EM radiation and or particles are what I've seen you refer to, and I would also refer to it as kinetic energy of particles, leave the simulated volume. So when all of that is left, I'm calling it absolute 0 Kelvin temperature, which of course we know from from other people's work that you can't quite get to absolute 0. You can get rather close, quite close, but in the simulation experiment, in concept, you can get there. Now, what are the results? I find it very interesting that the final density, when we get to absolute 0, all kinetic energy is gone, gives you an extremely interesting curve. At the very high initial bit densities, you get a very low, almost very close to zero final bit density and in the simulated volume. And you can say, well, what is going on here? I'm thinking that this is basically what you see if you run the simulation is a huge explosion. Everything is just going out in every direction. And when it cools down and there's nothing left to leave the simulated volume, you have a very low bit density. Now, if we go up a little bit more, go down a little bit more in initial bit density into what I'm calling the plasma range, you get a higher final bit density, but there's still sort of an explosion that occurs because in vacuum mode, nothing is contained. It just explodes out. And so that you're looking at what's left. Now, when we get down to, let's see, I'm trying to remember the graph, let's say about 0.4 to 0.2 bit density range, you get a constant value, which I find very interesting. And the end of my little speech is going to be in about 2 sentences. That constant value is about 0.23 of bit density, quanta density. Okay. Now, in other words, you start at 0.4, you go down to about 0.23. In other words, it's a flat line, okay, in that range. And so I'm also calculating how many nucleons are in the final simulated volume at theoretically 0 Kelvin. And it turns out that they occupy a very small percent. I haven't calculated it yet, but it might be like 2 or 3% or even less of the quanta in the simulated volume. Now let's go back to our everyday physics 101. A perfect vacuum is where you take those particles out. Those, let's say, hydrogen atoms, helium atoms, whatever happens to be there. And then you have what's called perfect vacuum. So the punchline is, and I guess it was more than 2 sentences, but the punchline is that in this range of bit density and final bit density, most of the quanta are not particles. They're the vacuum. In other words, most of the energy quanta are actually the vacuum, let's say at standard pressure and temperature, like we have right here in your room, in my room also. Period, end of story. So that is, and now I guess the accomplishment here is that we can systematically show in terms of the binary mechanic model of space, and steady vacuum in a way that perhaps had not been possible before. But I find it surprising. Like, if you read or listen to people talking about physics and atoms and so forth, they're going to say, well, it's all empty space there. There's a few atoms, one here and one there, and the rest of it's just empty. Zero, nada. Well, my work is showing, in fact, most of, well over 90% of the energy quanta is at nada. It's not nada. It's a whole lot of stuff.
Well, I'm not quite sure I understand, because you're saying that, if you remove all the recognizable atoms from space and you're at 0 Kelvin, you're at 0 bit density. Doesn't that mean this is like...
Well, no, it's not at 0. If get down to 0 Kelvin, the final, what I'm calling the final density at 0 Kelvin is a function of the initial. And so...
well, why would it be that? It's...
below the plasma.
If I'm doing a super cold experiment and I have a cloud of rubidium atoms that I'm trying to get to 0 Kelvin, which is what they physically try to do, yep. I would say that you have atoms still there. It's like that shouldn't technically change the bit density any. The temperature shouldn't really change the presence of the atoms, one would think, or do you think it does that?
Well, my working hypothesis, which is maybe based on a lot of ignorance, actually, is that the atoms, yes, are still there, as you intimated. But what I am saying is that when you get down to 00 Kelvin, or near it, in so many experiments that people are reporting and tinkering with low temperature work, the space between the atoms is not like nothing, okay? As a matter of fact, most of the quanta are the vacuums.
Well, in what sense? I mean, I can kind
less
of.
than 10% of the quanta are the actual atoms. So what we're saying is we have atoms at any temperature. Let's say below plasma level, okay, just because that's a whole nother topic, so to speak. But at any temperature, most of the quanta are not the particles that we've been studying, the atoms, the molecules, and so forth. Most of the quanta are what we have been previously calling empty space, or some in quantum physics call it the sea, the vacuum sea, the sea of virtual particles.
What about those of us who advocate an ether? We call that the ether. Would you say that that's what we're talking about?
Well, I would be most interested. I wish I had the specifics to show the graphs and everything. And
well, we can do that next week, but the discussion is interesting.
Yeah, well, I would love to hear what the ether people, how the ether people interpret this. And they might say,
as an ether person,
this
I would say, I would basically agree with what you're saying, although I wouldn't say it's anything to do with bits. I would say that as an etherist, we fundamentally, and people disagree about what this thing is, but that there would be some fundamental particle which is not an atom. Like, that's exactly what you said, that your quantum, whatever you're saying that is, maybe it's just a matter of semantics here. Whatever the heck you're whatever the heck you're calling quantum, we're calling the ether particle. And for etherists, it would be some physical particle. And for me, that particle would be specifically a combination of an electron and a positron. So your quantum unit, or if somebody else is here, they might say it's just quantum ball. Someone else might say, but if there's some kind of particle. But this is a little different from binary mechanics, because that would imply an actual physical representation. Now, it could be that even as an etherist, that my electrons and positrons still have to have a representation inside a computer. That's certainly still valid. But I think that's still different from your binary mechanics, where you're saying that some conglomeration of bits in your computer represent an electron. I would probably say...
And even more importantly, as far as mass goes and atoms and so forth, nucleons, or protons and neutrons. Now, what you're saying is not necessarily very different from what I'm saying.
No, I don't think so.
I'm saying that the particles that I've defined operationally as so many of certain kinds of M&L bits, and if you have those within a spot cube, you've got a proton. Okay, and that's just defined that way, and it has certain defects and limitations and whatever. You also define a particle. You combine it, this bit with that bit, and then you get a neutron or the particles that you define. I've read one of your articles. So we're not entirely in different worlds there in terms of the kind of thing we're doing.
Physically, I think it works the same.
There's a whole bunch of quanta which are not formed into particles that are there.
Yeah, that's
what I read in
commonality.
your work, there's just nothing there but the Spaatl cubes that could have something in them or not. So what I'm saying is that yes, the individual quanta can aggregate and form particles, particularly nucleon particles and neutrons and protons, but that most of them, most of these little quanta, are not forming particles, and they're what's left if you take the particles out, like you pump the atoms out to create a vacuum. The vacuum is not nothingness. It's all of these quanta, which is actually about 90% of the quanta that you have. And
yeah, that sounds an awful lot like this whole dark matter mystery.
Oh man, I'm glad that you brought that up, and I didn't say it because I'm saying this is your dark matter. I'm talking about more than 90%. I wish I had the percent with me, but I didn't quite finish it before today's program started. But like, there's a fly flying around here. That's why I'm clapping.
I thought you were giving yourself a clap.
No, I'm trying to kill a mosquito or some flying insect that's flying in front of me that I guess the resolution of the camera does not pick up. At any rate, in other words, this more than 90%, it would seem to be even closer to maybe 95% of the quanta, as I've defined them in binary mechanics, which could be right or wrong. All right, let's not assume that everything I postulated is correct. It might not be, but
I think that we can agree that there are quanta, right? Because once we agree there's quanta, then there's kind of a question of how do those quanta combine to make, say, the visible stuff, right?
Okay, well,
so you have to, you have to explain
laws of binary mechanics.
Yeah, and you have your binary mechanics way. Although as a physical person, that's kind of my shtick. I like to explain everything in terms of, say, billiard balls and physical things. Yeah. And I know physically that we recognize that the electron and the positron exist. So that's why I like starting there. Now that's kind of a philosophical starting point that I like to start with things that we can actually see. Although I think you're free to speculate as to how what the implementation level of the electron and the positron are. So that's why I still entertain the fact that we could be in a simulation. However, I don't particularly subscribe that some particular arrangement of say bits represent that. It's possible. Although as a computer scientist, I kind of prefer implementing things on using bytes and logic gates and that sort of thing. Sure. Because you're still giving the physicality to your actual electron, which is actually some physical arrangement of bits in your computer, rather than just being an arbitrary thing and running with code, I would say.
Well, the electron is the electron spot in my work, and it's a composition of two or more quanta. Okay, so a spot that doesn't have this requisite number of quanta is not deemed to reach the threshold to be called an electron and observable as an electron, which might be similar to your thought pattern as well. But yes, the fact that so many of the quanta are not in particles, that's possibly your dark matter, but that certainly is not this idea that you have the atoms and everyone likes to say, 90 some odd percent of our volume is empty space. Well, it's not empty space. And by my work, it's filled with quanta like crazy. Okay, and the quanta that aggregate into what we are calling observable particles is a very small fraction of that. And so this sort of vindicates those theorists in the past who've talked about the virtual particle, the sea of virtual particles that exist in the vacuum. And
yeah, I keep on mentioning
even
that,
dark matter. Sorry.
Well, I keep on mentioning that the mainstream does refer to this virtual sea, and there's a very interesting experiment called the Lamb shift experiment, which mainstream agrees proves that there must be a sea of positive and negative charges that electrons are moving through in order to observe this, what they call the land shift. And I feel that is actually a very direct bit of experimental evidence showing that we do in fact live in a sea of charges, and that there's really nothing virtual about that sea. So I'm just saying that there is direct evidence of a positron electron sea.
My work does agree with your thought pattern, because there are supposedly in my work two kinds of quanta bits, M and L. And the M have the property that they either carry a 1/3 plus charge or 1/3 minus charge. And so that when we're talking about most of the quanta in any volume, let's say here on the surface of the Earth, not to talk about outer space, which is a whole nother ballgame, by the way. We are in a sea of plus and minus charges, exactly as you were describing. And
well, now the question is, you know, basically, how can we separate out, say, two theories? Let's say we have theory A, which says that the electron is the fundamental particle, and that the empty space is actually a sea of basically electrons and positrons. So that's one possible theory. And in that theory, the electrons would just basically be fundamental. And then we have theory B, where we have your theory, where we have a bit mechanics theory, which says that an electron is, say, your electron spot. And I'm not sure how you describe your positrons. Positron spot, and
spot too. And so if those two spots, and by the way, there's 8 spot types, and so the 6 others are quark spots, d-quark spots specifically. So,
although I would think that your theory would predict that at some point we would be able to find a fractional 1/3 charge.
Well, there's I'm not up on reading the specific papers recently, but as far as I know, physicists in the mainstream accept the fact that there is a fractional charge, 1/3 charge.
No, I don't think so. I mean, they've actually done a lot of work because it has to do with finding actual quarks, but not unless you talk with Dr. Lucas, in which case he is convinced that some of the scattering data shows that it's true, but I'm not sure that you could ever tell a difference between a charge ratio and an actual fractional charge. My point has always been, it's like, how do you detect a fractional charge? Well, say in a proton, you know, you can definitely shoot things at the proton and you can see how they react. And I think you could tell that there are multiple objects in there, and you could tell that like there's like 2/3 positive charge and 1/3 negative charge. But is that due to an actual fractional charge, or is it due to there being just 2 positive charges and 1 negative charge, but still being whole charges, right? I would think that you would be able to tell that there's 3 pieces in there, but you wouldn't be able to tell, say, that there's a 1/3 positive charge or a 1/3 negative or 2/3 negative charge in there. I just don't think that you would be able to. Now, I could be wrong there, but
well, you're ahead of me on the literature on that, so I'll have to defer to your descriptions.
Although, you know, see, if they had actually discovered a fractional charge, that would be the #1 piece of evidence to say that quarks are actually real. But, you know, all the evidence and all the excuses given by the mainstream is that we cannot see that 1/3 fractional charge because the energy required to break apart a quark is such that it would give it the full charge again. And so but that's kind of an ad hoc excuse, saying we can't find it because, well, we're not supposed to find it, right? Or it can't be found is basically the excuse that's given. Although I would point to that as being basically something which has been experimentally explored in great detail, because I'm sure lots of people have tried to find the fractional charge, to the point where I think it's pretty much proven that there is no fractional charges. So if you have a theory which is pointing towards fractional charges, I would point to that as being something that's not correct. It's predicting incorrect empirical results. That it should say, to match empirical results, I would say your theory would have to have an explanation for why we don't see fractional charges, or why a fractional charge can't exist. Would be more in line with the empirical data. Now maybe someday someone will find a fractional charge, and then all of us who are in the not fractional charge camp will have pie in our face. But until that day, I would say those of us who are in the camp that say that such fractional charges cannot exist at all would prevail. And see, I would explain, this is the reason why fractional charge cannot exist. And, you know, in my strange world, where we have the world being run by, say, a computer that's running at a fixed clock rate, that at a certain point, things can either exist or not exist. Really, there can be, at some point, there has to be something binary, like your binary mechanics. At some level, there has to be some sort of binary representation for things. So that binary representation happens to come with the two phases that an electron can exist in, right? So let's say that this is the 1 state and this is the 0 state, basically. Now that could be represented by something in the computer, but basically there's going to be just like an on and an off state for the electron, right? Now the reason why we have the electric field and to have a complete description of physics, you really do need a physical explanation for what the electric field actually is. And what I feel that is that when you have this electron is basically flipping from 1 to 0, and maybe it is actually physically getting larger and smaller or something. Maybe it's taking 2 spots and then 0 spots in the computer. But that will send out a wave. A wave that if there's another particle here and this then goes that, it's gonna push the other particle away, kind of thing. So it's gonna. But fundamentally, that can only happen at one frequency. That the fastest it can happen is at the frequency of the clock. And so that is going to. So every electron will generate the wave at exactly that same frequency. There's no other frequency that's available. And that wave is actually the electric field that we see around an electron. So I am saying the reason why that cannot be fractionalized is because it is running at a fixed clock rate. There's only one rate it can run at. And there cannot be a 1/3 of that wave, because it's the electron can only do this. It can't go 1/3. It's got to go the whole way. So it can't put out only 1/3 of its charge. It has to put out the full charge, because it's a quantized action, right? So that's the reason why out of an electron we must see the full charge, and we can never see a fractional. There will never ever, that would be a prediction of my theory, that you will never ever, cannot ever see a fractional charge coming out of an electron. I mean, the most you could change it is if you could stop the electron from pulsing, then it would be like 0. And then you'd have 0 charge. So it's either 0 charge or you have the full charge. You cannot have any fractional charge. It would be physically impossible in my world for electron to put out anything less than a full charge.
Okay, let me throw something else at you. Now, in my so-called fundamental constants derivation tree, which is an illustration you no doubt have seen, it was in my first presentation here. I call the fractional charge elemental charge. And the reason why is because in my brief look at the literature in physics, which is secondary sources, again, I haven't delved into the primary sources as I mentioned on this subject a moment ago. But in those secondary sources, there are two uses of the term fractional charge, and that's why I chose to use the elemental charge to distinguish what I'm talking about compared to these two uses that you see in the literature. Because if you say fractional charge, people will wonder, is he talking about A or B? Now, A has to do with the individual particles, like say the electron, and can we observe that, and so forth. The B is more let us say larger mass assemblages, which high energy collision experiments have apparently detected, which are said to also exhibit under certain circumstances fractional charge. Now, one way to possibly demonstrate that is the amount of deflection in an electric field, in a known electric field, of such objects. And I don't think this work has been done, but would indicate possibly that this whole aggregate object that they've identified, or claim to have identified, has a fractional charge. So that would be a second body of data related to the idea of fractional charge. These larger aggregate objects of, I think there's like pentaquarks, with 5 quarks instead of just 3, and so forth and so on. But again, I haven't delved into that literature. Perhaps if you or someone else in down.
Well, I'm just kind of curious. I mean, does anything in your actual binary mechanics rely on the fractional charge, or could you just say, okay, the fundamental charge is like 1, and everything still works? So, because I think maybe you might be influenced unnecessarily about the evidence for quarks. And certain theories like my own basically say that quark doesn't exist. I mean, that is my definite prediction from my theory, that definitely quarks don't exist, and I still haven't seen any physical evidence or experiments that's actually able to tease these things out. I mean, still, even physics now, there's still people who might question whether quarks are more just an interesting nomenclature that they can use to, as a taxonomy, classify particles, but they actually don't exist. I mean, for a long time, people really thought that. Even the creators of the quarks kind of thought that, but now people have kind of come to accept that quarks are actual things, and that but in spite of the fact that we've been looking for them for like 30 years and no one's actually managed to isolate one. So I'm kind of wondering about, so do you think maybe you have been unduly influenced? Could your theory be modified to just take a whole charge and not really change anything about how your binary mechanics system work?
Well, that might be possible. In the derivation of fundamental constants tree that I mentioned, it turns out that everything has to be consistent with everything else, or else it all falls apart. And it turned out that the mass of the m bit, or of the individual quanta, is 1/3 the mass of the electron rest mass. And so that it would seem then that if the m bits have plus and minus charge, the ones with the minus charge composing the electron, when in the electron spot, you would then have the fractional charge. And so this would make it all consistent. Now, that would be one.
Well, maybe let's just question that little bit there, because that's kind of presuming that electrons are an addition, like you take 3 little bits and you add them together and they make the whole thing. But that may be kind of a naive an idea. I mean, there could still be that your electrons are still made out of things that are composed of, say, 1/3 mass, I suppose. That doesn't necessarily mean that those things came with 1/3 charge. It could be that when it comes together, then it generates the electric field, which is always a unity. It could be that your fundamental mass particles, it's possible for them to not have charge at all. I mean, this is always a fundamental problem I've always pointed
that's
out.
Possible. Yeah. And I really
that an electron can't be made out of charge. That's always been my point. That an electron cannot be made out of smaller charges, because if they were, then you have this problem that they're going to repel each other, right? If an electron is in fact made out of 3 particles, those 3 particles would be repelling each other, and you would have a problem.
Okay, let's stop there. Here's a good point to add to the mix. I've heard you mention that, well, that that if there were smaller constituents, they would repel each other. In the binary mechanics model, in the electron spot, these 3 m bits, if an electron spot contains 3 of them, are in different spot units. The only way, so and they do not influence each other according to the electrostatic repulsion bit operation in binary mechanics.
So then you're saying that the electrostatics
so they would not repel each other.
Well, then you're saying that they don't have charge.
No, they have charge, but
the thing is that charge is defined in terms of the electrostatic repulsion, and if you don't have electrostatic repulsion, I would argue you don't have charge.
Well, there's the missing ingredient in what you're saying, that what is the electric potential? In binary mechanics, the electric potential is the m-bit field. And only an adjacent m-bit can influence the, and this is how the electric charge was derived, in fact. In the scalar bit operation, only an adjacent m-bit to an existing m-bit would have the effect of accelerating an m-bit and giving your repulsion type of effect, or dispersion of charge effect. So that is consistent. Perhaps if we go back to the very beginning, you mentioned the positron and the electron. Well, the positron was basically discovered, as I understand it, with a pair of Dirac equations of opposite-handedness. Okay? Now, those equations have all these crazy spinner...
You're breaking up a little bit there, James. I'm sure what's going on with your internet connection. Yeah, you're breaking up. I'm not sure what's going on. It must be the man. You're getting too close to the truth. And I'm hearing an echo as well.
Let me turn down my volume here, because I'm not using the earphones.
Well, you were fine before.
Oh boy, I wonder what happened.
Well, that's a little bit better. Do you have headphones?
Yeah, I have headphones. I could try to use them.
Now, it's a little bit unusual this morning that we don't have anybody in the live room except for us this morning. So if you're watching and you'd like to participate in the conversation, you can go to live.naturalphilosophy.org. I think maybe people are taking it easy for the Thanksgiving weekend, or either that they're all shopping. So what if I mute your mic and then bring you back? Okay.
Oh, my mic? Oh, okay. My mic is now... But you sound staticky. Like you're static.
Yeah, maybe what you can try and do is you can try exit and then come back. Maybe sometimes that helps. Yeah, you've muted yourself. And now we can't hear you.
Unmute my mic. When my mic is muted, you still have the static.
Yeah, I would suggest, why don't you exit StreamYard and then come back in and see whether that cleans up your connection.
Okay. Bye-bye.
Okay, see you in a second there. Yeah, I'm not quite sure. Sometimes we have problems. We don't know what quite causes those problems. But, you know, we've been discussing, debating the nature of, you know, how space works and actually the nature of charge, which I think is an important thing to be talking about. It is one of the things that mainstream basically cannot really explain. And I think, but between me and James, I think we would both agree that, you know, there's something about the actual basis of how reality is being rendered, and I could certainly be on a computing basis. Now, I just saw an article, and I'm going to share this here. So in Google News, there is an article here about computing here. Physics. They've got a lot of quantum computer stuff here, but I thought I saw an article on, yes, our universe may be part of a giant quantum computer. So this is another thing in part of simulation. And there's quite a bit of articles on quantum computing itself. That everything should be viewed as a quantum object. We don't need to look at subatomic particles or qubits. We're already there. Everything is quantum. So the entire universe is a quantum? I don't think so. I could definitely think there can be quantized below that. Like 2 grains of sand, it would be a quantum separation. Consider the entire universe quantum? That's a little bit going. That's going a little bit far there. Okay, there you go. So are you back, James? Well, I'm afraid you're still breaking up just as much as before. Say something, James. Yeah, unfortunately, you're breaking up. I still can't hear you, which is weird. Yeah, maybe you should try your headphones if you got them. See here, we got some comments here. So Aubrey Enlay says the Earth measures flat and level, no curvature. Well, gee, I can go look at the edge of the Pacific Ocean and see. Not hearing me. Let's see here. So you can't hear. Now you can't even hear me, huh? No. I think you're getting worse here. Connection is falling apart. See, I can barely hear you there. Say something. You know, talk. You're breaking up. Dude's going to chat here. It's like the universe has conspired to break your audio. Well, I would suggest that you try and get some headphones. So hopefully you can try that. But to respond to this comment here, so I'd like to know what experiments have been done to measure the Earth's flat and level. That would be my question. So if you have some evidence to support that, put that in the chat. I'd be curious to see what you've got. Okay, you've got your headphones on. Can you hear me now?
Yes, I do, buddy.
So you can hear me, but we can barely detect that you're talking. Well, this is terribly frustrating. Yeah, well, I think we're having technical difficulties. But since there aren't too many people participating in the chat today, maybe we'll just end things a little bit early here, since James seems to be having some technical challenges here. Yeah, I think we're just going to have to end early, since you're my only guest and I can't hear you anymore. But let's see here. Let's see, got something in private chat. Okay. I probably need to go take care of my mom. She's probably going to wake up any time now. So thanks, James, for participating in today's chat. Yeah, we'll be stopping here a little bit early for the holidays. So, but everyone have a wonderful beginning of your holiday season, and we'll see you here next week then.